every positive integer can be decomposed into a product of primes. So we have, for example, we have 84. It's 2 to the power of 2 times 3 to the power of 1 times 5 to the power of 0 times 7 to the power of 1 times 11 to the power of 0 times 13 to the power of 0, and so on. To make a point clear, what's a prime number? A prime number is a natural number which is greater than 1 that has exactly and only two distinct positive divisors, 1 and itself. So in this case, 7 is only divisible by 1, and by 7 there's no other number that 7 can be divided with to get another number, another natural number. We could divide 7 with, I don't know, 2.5 and we can get a number, but a natural number we can't get. All right, there's an interesting law of prime numbers that says in order for a number x, so we have a number x and we have a number y, in order for x to divide y, which is written like this, or you can write it mod of yx is 0. So in order for a number to be divisible, all primes in x prime factorization must be in y's prime factorization. So if we have x, which is 2j0 times 2 times 3j1 times 5j2 times 7j3 times 11j4, and if we have y, which is, let's say, k0, k1, k2, k3, 11, k4. So in order for x be divisible by y, then for all of I, the ji needs to be less or equal than ky. So every positive integer can be expressed uniquely as a product of prime numbers raised to a certain power. So if we have 60, so what is 60? It's 30, it's 15, so it's 2 to the power of 2. So 15, so we have 13, we have 15. 15 we can't divide with 2 anymore, so we can only divide it 3 to the power of 1 times 5 to the power of 1. And another case is, for example, 24, which is 2 to the power of 3 times 3 to the power of 1. So when one number x divides another number y, which is written again, as I said, it's written like this, or, so for this to work, all primes in prime factorization must also appear in this number's prime factorization with at least as high powers. So if we have two numbers, x being 12, and 12 is 2 to the power of 2 times 3 to the power of 1, and we have y, which is 72, which is 2 to the power of 3 times 3 to the power of 2. Now, these numbers are x is divisible by epsilon because 2 is less than 3 and 1 is less than 2. Basically, it needs to be less and equal than. Another number that we can test this theorem is 12, which is 2 to the power of 2 times 3 to the power of 1, and y can be 18, which is 2 to the power of 1 times 3 to the power of 2. So now in this case, we can see that, okay, this is 2 times 2 times 3, and this is 2 times 3 times 3. We can divide with 2, we can even divide with 3, but because the last prime, that is this number divisible with this 2 for x and 3 for epsilon, they are not divisible by each other. All right, so let's now talk about concepts of greatest common divisor and the least common multiple. So the greatest common divisor of two numbers, x and y, is the largest number that divides both x and y. Again, we can represent these two numbers as in terms of prime factorization. So we can have here 2j0, 3j1, 5j2, and we can also have y, which is 2k0, 3k1, 5k2. So the greatest common divisor of these numbers, x and y, is, so it's a number that's a minimum between these two exponents. And we need to, for each prime factor, we need to take the minimum exponent that appears in the factorizations of x and y. Again, let's have 60, which broken into primes is 2 times 2 times 3 times 5, and this is 2 to the power of 2 times 3 times 5. These are to the powers of 1. We can have y, that's 45. It's 3 times 5. It's 3 to the power of 2 times 5 to the power of 1, because we have only 1 5 here. So what is the greatest common divisor of these two numbers? X and y. The greatest common divisor is 2. So we have a minimum number between 2 and 0, because we have 2 here and 0 at y, times 3, minimum between 1 and 2, and times 5 with a minimum between 1 and 1. All right, so what's this? It's 0 here. So this is 0, this is 1, this is 1. It's going to be 2 to the power of 0 times 3 to the power of 1 times 5 to the power of 1, and it's 15. So the greatest common divisor between these two numbers is 15. Now, we also have the least common multiple. So the least common multiple of two numbers, x and y, is the smallest number that is divisible by both x and y. Again, if we break this into factors, so if we break this into factors, it's the exact same thing as in the greatest common divisor. The only difference is it's a maximum. We are looking for the maximum exponents here. Times 3, again max, between j1 Hemo space here. But yeah, I think you understand. Instead of looking for the, I took too much space here. Max j2, okay, and so on. So it's the same thing, but the difference is we are looking for each prime factor p, we take the maximum exponent. So what do we have here? And we can take, for example, the same two numbers that we have here. I'm just gonna rewrite them. So we have x 60. I'm gonna take the same two numbers. 60, which is 2 to the power of 2 times 3 to the power of 1 times 5 to the power of 1. Y 45, 3 to the power of 2 times 5 to the power of 1. Same thing here, but instead of taking the 0, I'm taking the 2, so it's going to be 2 times 2 to the power of 2 times 3 to the power of 2 times 5 to the power of 1. It's 4 times 9 times 5. So what's this? It's 180. So this is the smallest number that is divisible by both 60 and 45. And another thing is, if we multiply the greatest common divisor and the least common multiple, what are we gonna get? So I'm gonna do this here. The greatest common divisor, x and y, times the least common multiple of x and y. So it's 15 times 180. It's 2700. And if you also multiply x by y, it's 45 times 60. It's again 2700, which confirms the relationship. Now, how to check whether a number is prime? So we have the basic method, which is then the naive method. For example, in order to check whether, let's say, a number such as 1, 3, 3, 7 is a prime, the naive way would be to test whether this number is divisible by any number between 2 all the way to the x minus 1. And how it works. So we will basically loop through all integers. We can also write a piece of code which loops through all the integers from 2 to n minus 1, and then we check if n is divisible by I. And if it is divisible, we return false, which means that the number is not a prime number. This may be a more complex example, but what if we put 7? So our divisors would be 2, 3, 4, 5, and 6. And we go 7 divisible by 2, no it's not, by 3, no it's not, and all the way to 6, because we find no divisors, 7 is a prime. So here we basically have the code for the naive version, in which we get a number. If it's less than 2, we return false, but then we look for the range between 2 and then. If any of those numbers that we loop with is divisible by the initial number, we return false, otherwise we return true. But there's a better method, and there's a more optimized method. So how does the optimized method work? Like this. So we are checking all the numbers from 2 up to n minus 1. So if we have a really large number, this will be a really large loop. But what happens basically here is that at a certain point we can stop at the square root of n because of a mathematical insight. And why can we stop at the square root of n? Because let's say we have a pair of divisors a and b, and we know that a times b is n. So we know that a times b is n. So if a is greater than the square root of n, then definitely b will be smaller than the square root of n. We have two divisors of a number, and for every divisor a which is greater than the square root of n, the complement divisor b needs and must be smaller than the square root of n. So we only need to check divisors up to the square root of n. And for an example, we can take 37. So the square root of 37 is around 6.08. So what are our divisors? Our divisors are going from 2, 3, 4, 5, 6. And now we can only loop through these numbers. 37 is prime because it's not divisible by either one of these. But we can take another example in which n is 36, and we have the same thing. 36 is 6, so we have 2, 3, 4, 5, and 6. And we check. The first one is 2, and we know that 36 divisible by 2 is 18. 2 is one divisor, and 18 is another, and 18 is bigger than the square root of 6, so no need to use 18. We already know that if this number is divisible by 2, then we have a number that is not a prime number. And the code for this looks like this. So it's a optimized algorithm.